Oh, my roommate had 3 at the gym at 5 too.
They're so cool. You know, I came to realization. Like, who's the most like, I'm gonna wear when I go to the gym, I'm gonna wear sweatpants.
Sweatpants over like.
Didn't do anything
Yeah.
the first time.
Wearing, yesterday I was wearing capri leggings under my jeans.
Like it's a class?
Yeah.
This stat, whenever it was like,
Okay.
the wall at the top of his release, it's like, he's like 9 feet, 2 inches tall or something. Yeah,
It's gonna be so bad. What is
He's like,
our lab?
It's just like an unblockable.
Yeah.
The whole piece for me.
Basically a 7-foot yeah, actually, the NBA is actually kind of interesting.
Well, I'm projected, might as well go outside, right? Yeah.
Show off on the.
Let's do it again.
Yeah.
Alright, so I was thinking I'm a little lazy, so, for the homework assignment, remember I was talking about going to the other professor's office hours and talking to them? So in the next, 2-3 weeks, that could be your homework assignment. I'll give you 10 points for it. You can go talk to the professor. And then give me like a half a page write-up, either, that means that you went to their website and read their little bio, what the research that they do, or you talk to them about it, right? Or if you, like I would even say go and ask about some topic in the class, and just tell me like, oh, we went over this, blah, blah, blah. I'll give you 10 points for that, yeah, and that'll be an extra credit.
But you can either ask them about their like degree or about a question in class.
Yeah, or about like if they do research and stuff like that. It doesn't have to be me, it can be anybody. Already.
So like 2:30.
Oh, I see that.
Yeah. Your wireless now. This system. They should be for class today.
Appreciate it.
You're welcome.
So last week, I kind of had like, I was looking through you guys' questions that you guys submitted at the end. And one of the things I wanted to bring up there was, so about like, what's the deal with, or what's the importance behind of them moving the molecules into the different compartments, right? Remember I talked about the big change in the sodium potassium pump, where you're pumping the ions in different compartments and enriching them. The other one is your proton pump, which is moving your hydrogen, right? So your cell is basically gonna put in the work to enrich the hydrogen. It's gonna do the work to enrich the sodium and the potassium of the environment. Because it's then gonna use the concentration of those molecules to drive the movement of something that it wants to do against the gradient, right? So it's like in one of them, they were saying, you build up the hydrogen on the outside, you're pumping it out. So now I want you to think about it, there's a hydrogen pressure that's trying to come into that cell, like it wants to drive itself in. And what you're doing is you're using that strong force of getting the hydrogen into your cell, that you're attaching a shear, you're basically gonna drag along with it, the sugar into your cell, right? So that's where we can use the gradient of one molecule to give it a driving force for a molecule against its gradient, or even if it doesn't have gradient, it'll help you enrich it. So that's kind of the big picture of the big mechanism, the reason why you do it is to do that kind of thing. I think the other one is the, you guys say neural, they'll talk a lot about it for the brain impulses. And that's where you have a big one where along the arm of the neuron, they're basically kind of using these ions to change the charge of it. And that's how you have your electrochemical potential, and that's how the signal gets transmitted. But they don't enrich them on the outside. When it snaps, it will let the signals come in. It changes the charge of the cell, and that's how you transmit the signal. But for our class is know that you can use these to move the chemicals either with the gradient. In some cases, you move them against the gradient, and the cell takes advantage of any gradient that it has in order for it to quote, like get work for free out of those gradients. That'll be the big step for that one. I think this week we have, this week is homework week, right? Or is it in class? No, it should be homework. We have homework this Friday. So we have homework. I'll set that up for Friday. Let's get into today's topic, which is energy and metabolism. All right. Here we're going to be talking about how the energy flows through the system. We're going to talk about different forms of energy, and we're going to go a little bit into the laws of thermodynamics. I want you to be thinking about, I think we're going to go a lot into depth about potential energy versus kinetic energy. And then for the molecule, basically for us, like I want you to be thinking about potential energy to be almost like in our lives, it would be like our food. That's a potential energy. And then kinetic energy is actually when you start moving around your muscles and you start burning that energy off. Okay. And then after that, we're going to do a little bit of math at the end, talking about this delta G, about the free energy. And that's one thing that's going to help us kind of show when we have chemicals that, or reactions that we have a reagent, and as it goes through this mechanism, it should produce a product. In some cases, it wants to do it. In some cases, it doesn't want to do it. Like it's energetically unfavorable. And that's where you're going to see that a lot of enzymes are going to come to this to really help us out. All right, so we're talking about metabolism, especially for ourselves. We're talking about all the chemical reactions that are happening within us. From this is a really huge chart. Don't worry about memorizing this one, but what they want you kind of to see is that in order, we're going through processes, we're making things, we're also breaking things. The things we've talked about before was amino acids and DNA, right? Those are things that every time a cell wants to divide, we have to make these number cables, we have to make all our proteins. When we're time for us to eat, phagocytose or eat some either ourselves or other cells, that's our time we have to get those peptides, those DNA base pairs, and we start chopping them up. So for this, here you can see a little bit of the urea cycle, and you're basically keeping track of your ammonia or like your nitrogen. As you can see, your nitrogen pool, that what goes into your amino acids, right? Because you have your amino groups, also the side chains, and this will be the thing that you can build up and get your proteins. As you build it up, like I said before, you also eat this. You also eat your proteins. This all in amino acids. These amino acids can get even further broken down and releasing those nitrogen groups from the amino acids themselves. This then also can get to the point where those amino groups that we're talking about, or those nitrogen groups we're talking about, within us also gets included into this urea cycle. And this one actually gets all the way till you can actually pee it out. That's how you clear it from the system for the old stuff. For this one, acetyl-CoA. This one showed up in the midterm. I don't know, that surprised me because we never talked about it before, but somebody answered acetyl-CoA for some questions. So that was kind of weird. For this one, we're talking about, it's basically one of the reagents. It's an acetyl group, or it's the enzyme, but we're talking about how you're basically balancing those within the citric acid cycle. And there, our waste product is going to be our CO2. Those are the things that we waste. All right, let's go. So we're talking about metabolic pathways. Here we're going to be talking about how basically these molecules can get modified over time. So in this case, we can have a starting molecule, which could be something small. It could be something big. And depending on the different enzymes, so this will be proteins that your cells specifically made. Different cell types will make different types of proteins, but you'll basically create a pathway that a molecule would progressively get modified, and each subsequent reaction actually ends up producing all the way to you produce your final product. For this one, let me think. Like an example of this would be like, let's say our starting molecule would be an amino acid, right? An amino acid goes through, it gets linked up by the first enzyme into your tRNA. Remember, it gets glued into that. On the next step, your tRNA carries it over to the ribosome. Working with the ribosome, it'll glue it to the previous amino acid that was at those APE sites. Once you do that, you start making your amino acid chain. Afterwards, you release it, and your final product is going to be your polypeptide chain, right, or your protein. So you go from single amino acid, these enzymes push you forward, to eventually end up producing a long protein. All right, remember, purple slides means you got to memorize it. No, I'm just kidding. So these are the charts that they normally use to talk about these big pathways, to talk about the reagents. To be honest, this is one of the things that they used to have in my biochemistry department, and I love the way that they drew them, because it gives you, like, you can follow, like, your molecules coming in. Corticoids, you know, we talked about NADHs, there's your aspirin. So you can basically transition from, like, a base pair like ATP can get modified to go into your DNA, right? That's your ACTG. Also, with the ATP itself, you can use those 3 phosphate groups to act as an energy molecule, right? As the adenine has 3 phosphate groups, and it normally can drop off that 3rd phosphate group to give it to a protein. You can modify different receptors, and it'll be able to produce. It'll function in a different pathway to actually signal. So it can be energy or it can be information. You don't have to memorize this whole thing, but it's actually pretty cool. So for this one, when we're talking about making and breaking, these are going to be the 2 key words. Feel super comfortable with these. I'm going to add these to our word bank. So we have here our anabolic pathways. So this one I used to remember because I don't know why it reminded me of anabolic steroids, right? And this is when you're actually building things, right? So things are getting put together. Normally when you're building things, this is actually going to require for you to put in energy, right? So let me think, which one have we done? I'll show you some a little bit right now, but this basically requires anything in your building. Opposite to that, you have your catabolic pathways. I remember this one because the first part kind of rhymes with cut. So catabolic, you're cutting things, and this would be when you're breaking things down. So if we were talking about proteins, right? If I said amino acids and you're getting to protein, you're building something bigger. That's your anabolic pathway. The opposite to that is if you have a protein and you're trying to digest it and you start chopping it up into individual amino acids, it's your catabolic pathway. Oh, I rested. But so in this case, what is this? Anabolic or catabolic?
Catabolic.
Right, because you're cutting that big protein chain into individual things. And how about if we went backwards from here going that way?
Anabolic.
Yep, there we go. Awesome. How about this one? Going from glucose to making like these long sugar chains.
Anabolic.
Awesome. No, wait, what? We're building a chain. What did you guys say? Anabolic. Sorry guys, this cold is messing with me. I feel a little slower. I don't know if you guys, but all right. So we're talking about you can build things, you can break things, right? The next part is we're going to talk about the energy, and it's like that's the thing that's actually going to be able. It's going to do the work for us. In big terms, I want you guys to know these two, which is going to be kinetic energy, and then the opposite to that was going to be potential energy, right? So kinetic is normally when something's already moving, something in motion. Potential energy is it has the ability to do it, and you can either have the ability to do something based on either like your position. We're going to go through some examples for that, or the other one here. I want you guys to think about, like I said, if we talked about ourselves in the potential side, that's our breakfast, lunch, and dinner, right? That's where we have chemical energy that we can use. Until we start using it, it doesn't mean it's just potential energy. The moment you start moving, remember your muscles have to contract, all those little motor proteins need ATP to move forward. That's when you actually start putting it into motion, and that's going to be on your kinetic side. Yeah. All right. The other type of energy, part of this kinetic energy, is going to be your thermal energy, and it's going to be, if you look at the random movement of your atoms. For this, I almost want you guys to think back a little bit about when we were talking about water, right? If you guys remember water, it's sitting in a container at room temperature, sitting in a container. All the water molecules will basically be at the bottom, right? When you start heating up water, you start giving it more thermal energy, eventually you'll start getting it to boil, right? And that means that those molecules are bouncing around so much into each other, they can actually start bouncing off and floating away. The hotter it is, they start floating away at a bigger ratio, like at a faster rate, right? So that's going to be thermal energy. And then the way that we normally transfer this thermal energy is gonna be through heat. This I want you to think about like for, yeah, it could be like cooking, right? So you have water boiling, that has a lot of thermal energy, it's moving around. If you then put like an egg into it, you're gonna transfer the heat into your egg, and that's how you're gonna cook your egg. But all the energy is gonna go from that water into the inside of your egg, so you have a hard-boiled egg. All right, perfect. All right, let's go to the next one. Here's my slides. All right, so this one, I didn't draw the little chart, but I kind of want you guys to, you guys have the notes annotated a little bit. So we're gonna be talking about the two different types, right? You have your let's say, your potential energy and versus your kinetic energy, right? So then up there, you have your driver at the top. So you have potential energy and you have your kinetic energy. Right? Because your driver is not moving at all, if we measured his kinetic energy, you can see that that would be at 0. Technically, he's not moving, nothing's going on, there's no motion happening. And up there, what you find very high levels of potential energy. Right? And that's because technically he's at a state where, kind of like you see the picture on the right, the moment he jumps off, gravity's gonna pull him down and he has a good place to travel or he pick up that speed and build up that energy. So up here, the top diver, a lot of potential, very little kinetic. If we then imagine the next time point to be the guy doing the end shape, at that point, what we see is there'll be a transition going into, at this point, he has built up kinetic energy because now he's gonna be traveling at a certain speed. Because he's halfway down, he's also decreased half of his potential energy, right? So it means he still has the rest of the speed to catch up a little bit of speed. The last guy we're gonna be looking at is gonna be the diver who's already in the water. At that point, if we look at his data, what do we expect for kinetic, high or low? No kinetic energy, right? Because he's not moving at all. He's already stuck in the water, right? And how about for potential energy?
No.
Low, right? Because he's already in the water. Well, he could drown, but relatively it's weak, right? And then you can see here that the last step would be, here's where you have to actually put in work, which is climbing the steps to again build up your potential energy, like going all the way to the top. All right. Does this one kind of make sense to you guys? Yeah? All right. So just like never mind. All right, just like that, about when you have a, like the height was one way to do it, right? The other thing I talked to you guys about was food. So if you guys do me a favor, if you guys scan that, you can get to that survey, you can answer your question there. So which of the following is an example of potential energy? Never mind. I put the question on there for the next part. So you guys can't submit it yet. Okay, well, I messed up. I'll do it again afterwards. So for this one, if we're talking about potential energy, well, yeah, submit your answers either right now or you're gonna submit it at the end, because at the next part, you can do instead of doing the note cards, you can do the little write-up thing, yeah. So I'll check this out at the homework, but I want you to be thinking about potential energy means that, or potential, this is for a physical example. You can also think about it from a chemical side. Like I said, it's our food versus our movement. But I want you guys to get your answers at the end of today's class. All right, so the next part, we're looking at thermodynamics. And in this case, we're talking about how this energy actually gets transferred. So there's two ways to study it. You can do it in a closed system versus an open system. In a closed system, they don't really talk about it like you think about it almost like in a sealed environment. I think they used to call it like a calorimeter bomb. Basically, it's like, you know, the drinks you guys drink or the cups everyone has where it's like 2 layers of aluminum and it's air in the middle. That way you don't have any heat leaving or exiting the system. And then they normally have really fancy lids, and then they would, inside those chambers, you would have chemical reactions happen. And based on, the only thing that would come in and out of the system would be that you had a probe inside. And that probe was basically telling you the temperature. And then what you would do is you would mix two things, and inside of that, you would see either how much heat came out of it, or sometimes how much heat went into the system. And then an open system would be something like us, where there is no control. So right now, we all eat breakfast. After breakfast, as all our body's doing all the metabolism of digesting all the sugars, breaking down the proteins that we ate, breaking down the lipids in our food, right? We're doing all those chemical reactions. We're breathing. They're getting oxygens going in. You're making urea. All those chemical reactions, you're burning energy to actually make the thing happen. At the same time, you're also producing heat, right? But as of right now, your heat is going straight into the environment, and there's no way to measure it. So that would be an open system. So for thermodynamics, it's saying that, remember the first rule is that the energy is always conserved. So we can pass it from one thing can pass it to another. It could also change forms. The thing is that it can't be created or it can't be destroyed, right? Like for our case, we can have movement, but the only way we have movement is that we have to eat sugar, right? And then the sugar in itself had to be built up from carbon dioxide. And that energy is actually coming all the way from the sun, which is powering up the plant to basically, it uses its membrane to charge particles. The charged particles then help it power the ability to glue sugar together, right? So you can see all the way from the sun to us, the energy has been getting transferred from one to another one, from one person to the next, from one organism to the next, right? Sun, plant, and us, but there's no place for it actually being created or destroyed. All right. Skip that. I want to delete that slide. Sorry about that. All right. Now, so the way that the energy normally flows, it normally goes kind of like it goes in the way that it's called increases entropy. But I want you guys to think about it as it makes it more disorganized, right? So here I want you guys to think about almost like here's an example, like you guys' rooms, right? Somehow magically it can become, stuff gets moved around enough that by the end of the week it could be messy. But the only way to get your room organized is you have to put in what feels like a lot of work to be able to keep and keep everything in the right environments. This is at your level. When we think about the particles, or we're looking down at the molecular level, I want you guys to think about diffusion, right? Remember on Monday, what I was talking about, how if you put the molecules in a very tight space all together, because there is thermal energy and they're bouncing around, they'll start crashing into each other. As they crash into each other, wherever there's more, they're more likely to bounce into themselves and push themselves further away from each other. So even though you try to organize something like this, if you just leave it there by its own, you'll eventually have these particles actually start spreading out from each other, and that'll be your disorder that it's trying to go to. And for these, you basically don't need energy. They can do it off their own thermal energy. The only way you can stop this would be if you could, what the thing's called? It's like an ultimate zero. I forgot what it's called. But basically, you have to reach to the point where there's so little energy, not even the atoms are vibrating anymore. But it's like super hard to achieve that. All right, for the next part, so let's talk about basically the change of energy and how it happens. Different systems have different levels of energy, and we're going to talk about the energy is normally based on instability. So going back to the example here, it would be when we talked about our diver, right? So technically, because he's all the way at the top, he's the most unstable, right? If he moves to one of the sides off that shelf, he can also shelf the diving board. He basically has the biggest ability to release a lot of energy, right? The people that are already in the water, because they have very little potential energy or they have very small energy in the system, there's nothing, they can't do something big as the diver, or like you can't get that much energy out of them, right? And then what's going to happen is most things end up, I like to think of it almost like, if you imagine like random movement of particles, it's if they both had that behavior of random movement, particles that have higher energy or potential energy, when they fall off, they have, or small movements from their side can equal a faster way of falling off. Random movement on this side you're probably not gonna get any big kinetic energy to happen out of it, right? And that disorder, going from organized to disorganized, is also the same place of things go from being very stable. If they're stable, they're likely to fall off and they move from unstable to the stable conformation. So being unstable is your like your potential energy, right? And this is gonna be our high energy to low. For that one, just stick with sugar. That's one of my favorites. All right, let's go. So as things are changing, we're gonna use this basically energy or delta E, and that's so you keep track of how the reaction is happening. For example, here, which we are reactants, and then you're gonna end up producing the final product, right? If you look at how much energy is in the system, here you're gonna see that if you do the energy of the product when it's done versus the reactants that it came in, that change in energy will tell you if energy went into the system or if it came out of the system. In this case, right, we can talk about the energy. Let's say our reactant would be, again, my favorite, sugar, right? You have all the carbons stuck together, you have the oxygen groups, it's a charged particle. The moment you start digesting that sugar cooking up, you're actually bringing energy out of it, and then your final product at the end is your CO2 being produced, and that's like your disorganized form, right? So just like this, we're looking at your free energy or what's basically coming out of it. Again, you can talk about it from the diverge side, right? So here we're using gravity. We can talk about it from just individual ions or particles, and this would be like the diffusion. And then here would be, for example, like I was saying before, sugar, and it'd be broken down into CO2. When you do this movement from one state to the other one, it's if itself can release energy, then it's likely that, or it's easier for it to do it by itself, right? For example, the diver, which is on top of the board, if we drop him off that, or he walks off the board, he'll release all that energy. We don't need anything else. Kind of like we don't need an extra help or invest more energy into it. If, like for example, I'm moving him from a low energy state, like I said, I was doing the work, and I'm trying to move him back up to the diving board. At that point, he's going from a low energy state to a high energy state, right? Like he's getting organized. At that point, I have to put in work to move him forward. That means that reaction is probably not going to be instant, like spontaneous. Like it won't just randomly he gets pushed up. Like we have to put work into moving to the higher energy state. All right. So for this one, I want you guys to think about it from this related to the topics about catabolism and anabolism. This could be one of your questions when you write it in. So pick one of the states and then tell me how it kind of relates to catabolism or anabolism. All right. So talking about that energy again. We talk about it from thinking about how we can charge up that diver, right? In the exergenic state, it's like he's releasing energy. At that point, it's going to be he's top of the shelf, he's diving off. The final thing getting in the water, he's lost all that energy because he's turned it into kinetic energy, right? In his own motion. Opposite to that is we have these endogenic reactions, which means that going from your reactant to your product, we have to put work into it. And this would be, like I said, if we had to put him back on top of the diving board, we have to put energy to actually carry him up or move him up to give him to the high energy state. Just like this, you can also think about it, like I said, with sugar, right? So you have sugar on this side, high energy particle. As you split up that sugar and we eat it, the product that we make is CO2, and what we're getting out of it is a lot of energy, right? In order to get it back, we have CO2 coming into the plant. We use the energy from the sun to power it up, and we produce our product, which is sugar. Right? And you can see kind of we'll cycle through this with CO2 and sugar being produced. All right, so for this one, I want you to think about it as protein, or think about the proteins, right? In this process, is this exergenic or endogenic? So we're building something, right? Protein in our food, hint, hint. So it's basically stored energy, right? In our food, right? So that means that this is the high energy particle, has a lot of energy. As we eat our food and digest it, like we're going through this side, right? Which is we're breaking the amino acids down and we're actually getting energy out of them, you know? So that's the exo part. The spontaneous thing it's gonna be about which one, if you're going from high to low, it'll work, you can get it to work. If you're trying to go backwards and trying to build from this low energy to a high energy state, right, that's gonna be quite challenging, then it won't be spontaneous, we have to put work into it, right? And that's when we talked about, what does all that work? Our ribosomes, our tRNAs, our mRNAs, all of that has to work together. All right, same thing, I want you guys to do the same thing when we're talking about the sugar, right? So for sugar, here you have the small sugar molecules independently. We're trying to glue them together, right? In order to do this, you're going from a disorganized to an organized, right? That means that we're gonna have to put work into it, and it's gonna have more potential energy on this side, right? So that's endo, because we're gonna have to put energy into it. It's spontaneous. No, because we're going from low energy to high energy, yeah? So when you guys are looking at the molecules, be thinking about that, like, are you gonna be bringing the energy in or out? And what are the two states that you're jumping from? Yes. Oh my God, I was on fire today, guys. 30 minutes, nice. All right, so any questions on this stuff? If not, type it into your, to that form, submit it, that way I can get it. You guys don't want to do the jot down thing? I do have flashcards, you guys can do it to flashcards. Yeah, so we have homework tomorrow, homework on Friday. And that'll be covering up to the ATP and energy stuff, yeah. All right.